All right. Hello, everyone. Welcome back to another session of El Zoominario. Today, we are very happy to have Rene Flores-Garcia from UW-Madison in the Department of Physics. He is, Rene was born in Toluca, in Mexico, which is a city that is around about 40 minutes outside of Mexico City. Rene received his undergraduate degree in engineering physics from the Tecnologico de Monterrey, which is another city in Mexico. And he is currently a graduate student in the physics department at UW-Madison. And he works there with his advisor, Carrie Forrest. And he is intending to become an experimental physicist in the area of plasma physics. On a personal note, I can tell you that Rene is an accomplished guitar player, and with that, I am ready to let you take it away, Rene. Welcome, and thank you. We're excited to have you. Please go ahead.
Hello, everyone. Thank you, Daniel. So thank you again. Thank you, and Claudia, for inviting me to give this talk. I'm going to be talking today about emulating a pulsar in BRB. My name is Rene Flores-Garcia. I'm a part of WIPL. WIPL is the Wisconsin Plasma Physics Laboratory. It is located at the Department of Physics here at the University of Wisconsin-Madison. And so let me get started. So first of all, just a brief outline of what I intend to talk on today. So the first thing that I want to talk about is what is a neutron star? How are they created? What's the process behind neutron stars? And also a little talk about pulsars. What is the relation of pulsars to neutron stars? Because a pulsar is at the end of the day what we want to achieve here in Wisconsin. Then I'm going to introduce you to the Big Red Ball BRB, which is basically where we conduct these experiments. Then a little bit about emulating a pulsar. I'm going to be describing specifically the hardware. So experimentally, where are we in terms of creating not a pulsar itself, but how can we emulate it? And what can we do? What are the efforts that we have been doing? And then I'm going to finish the talk talking about some future steps, so some next work that we need to do. So without further ado, let me check here. So what are neutron stars? How are they created? And what are pulsars? How are these pulsars related to the neutron stars? So first of all, let's describe a bit how these neutron stars are created. So neutron stars are created at the end of a star. So we're going to describe a little bit the death of a star. So let's just start with a high mass star. A high mass star of a massive star is described as a star which has around or in between 7 and 22 times the mass of our sun. As you may know, these stars create energy through nuclear fusion, which means they combine light nuclei into a much heavier one. And they create more elements. So at the end of their cycle, they start creating this iron core, and this iron core starts growing. Then when this iron core becomes heavy enough, the star itself and the nucleus cannot sustain itself under its own weight, meaning the pressure cannot sustain itself any longer. It has become something very heavy. Nuclear reactions start happening in which the electrons and protons start colliding. And they start releasing tons of energy as well as creating neutrons and some other subatomic particles that escape this. Once it has reached a threshold value, this core releases a shock wave. There's a rebound in which the star explodes and it becomes a supernova. So right after this thing has become a supernova, this star or this past star, meaning it has gone through a high explosion, we are left with a nebula. So for example, here I have the picture of what's called a Crab Nebula. The Crab Nebula is located 6,500 light years away from Earth. A light year is the distance in which the distance light has traveled within a year. So we can see here this Crab Nebula, in which we can see what was once a massive star. You can see that there's lots of remnants. All of this is gas, is plasma. And let's move on a bit. So what happens right when the star is gone? Specifically for the type we are describing, for a type 2 supernova, the rebound or the explosion doesn't happen right at the center of this star. It happens at some at some radial distance from the center, which means the core is still intact. However, because of the great pressure and all these uh, energy being released, this core has compressed, creating what is known as a neutron star. This neutron star preserves the rotation of the father star, or the star that it comes from. However, because of conservation of angular momentum and because it has reduced in size, it is rotating much more faster. Another thing interesting about these neutron stars is that these neutron stars aren't really that big as the father star was. So for example, right here to the right, we have a picture that compares an average neutron star to San Francisco. This is the Bay Area. Neutron stars on average have a diameter of around 20 kilometers, which is not that big for other quantities that related to space, so they are pretty small. However, the interesting part comes here. In this neutron star, the neutrons and all the subatomic particles are touching each other. There is basically no space, no vacuum within that neutron star. So they can reach densities of 10 to the 17 and 10 to the 18 kilograms per meter cubed. So what does this mean? It means that if I were able to have a spoonful of these neutron star right here, I could have the mass of a mountain here on Earth, but all within a spoonful. So you can see that these are pretty massive. They are much more massive than the Earth, and they can, or most of the cases, they are much more massive than our sun, and they are contained just within this little sphere. Now, another interesting thing is that the father star had a magnetic field, which is also preserved. However, due to its fast rotation and the fact that the magnetic fields have squeezed in together, these magnetic fields, the magnetic field of a neutron star has also amplified. It can be from 1,000,000 to 1,000,000,000 times that of the Earth. So let me show you this peculiar movie. I hope you can see it, in which, well, the neutron star is supposed to be rotating, and then we're going to see how what you can see here, that beam of light, is its magnetic axis and its radiation coming out of it. Now, I'm not going to dig too deep into the core of what's inside a neutron star. It's still an active area of research, but it is believed that ions, electrons, and some superconductors might be inside, which is what is causing these very high magnetic field. Now, what's the story with pulsars? How are pulsars related to the neutron star? So let me begin a bit on the story of pulsars and humanity. And it all starts in 1967 with a graduate student called Jocelyn Bell. Jocelyn Bell was a graduate student at the University of Cambridge. She was an observational cosmologist, and she was studying radiation coming from outer space. And in her efforts, she found, or she detected, some radio pulses coming from outer space, but she noted that these radio pulses were pretty uniform in terms of how the pulse of the pulse length and the time period between these pulses was pretty uniform. So the first thought, because she didn't know what she was looking for. She wasn't exactly looking for that. That just arrived at whatever detection hardware she was using. The first thought was aliens are trying to reach out. They're trying to tell us something, but we can get it. It was until some time later, this is the original paper, that it was on which it was published, that it was not aliens. It was actually a neutron star whose axis of radiation was aligned to that of Earth, and she was being able to detect it as a radio source. So actually, pulsars pulsar is short for pulsating radio source. And another interesting story about this is that the discovery of pulsars led to a Nobel Prize in 1974, if I'm not mistaken. However, even though Jocelyn Bell did most of the work on this paper and she was the one who detected it, she did not get a share of this Nobel Prize. Instead, her advisor and some collaborators were the recipients of this Nobel Prize. It was a Nobel Prize in physics. So what's up with pulsars and neutron stars? Are all pulsars neutron stars? And the answer is yes, but not all neutron stars are pulsars. I want to tell you why. So we consider, or in literature, we consider pulsars as neutron stars in which the beam of radiation is directly pointing at Earth, therefore we can detect it. If that beam of radiation does not pass by or does not reach Earth, we might be able to detect the neutron star through some other ways. However, we do not consider it a pulsar. Also, another interesting thing is that as this neutron star rotates and rotates, it radiates energy away. And due to electromagnetic torques, the intensity of the radiation goes reducing, as well as the period of rotation. It reduces throughout time. It takes usually a few million years until enough energy has been radiated away in order for us not to detect it, which is a pretty long time. And so our understanding of pulsars is the following. It's called the lighthouse model because of this sort of lighthouse behavior that some ships see on the sea. As I mentioned, these neutron stars and pulsars have a really high amount of mass. Therefore, they can gravitationally attract some of the surrounding gas that was originally expelled from the star, comes back. And due to the rotation here of this pulsar, we have this plasma here, which travels at very fast speeds, and it is able to create a pulsar wind. Now, the pulsar wind is just this wind that's rotating alongside the star, but because of forces, it gets spelled out such as a pulsar wind. And the same thing happens in some other stars. For example, in the sun, we have a wind that reaches Earth and other planets, and something similar happens here, which is a product of how fast this is rotating and how it gets expelled. Now, another thing here is that even though we call them neutron stars, they're actually not stars, because we consider a star as a giant gas in which nuclear fission is happening and it's creating energy. And that is not happening here. Even though we have charged particles and neutrons, they are not quite going through nuclear fusion and radiating energy in all directions. It is a very specific beam of radiation in which the energy is going. So with that being said, we have described what the pulsar is. Now, how are we here at People trying to do that? What are we trying to achieve? So let me introduce to you the big red ball. Now, the big red ball is where we set up the experiment. This is an actual picture of the big red ball. This is located in Sterling Hall here at the university. It is an aluminum sphere. It is 3 meters in diameter. And you may say aluminum's not red. Why is it red? It's because it has some insulation here in order to prevent the outside temperature to affect the experiment on the inside. And just so that you can see how big this big red ball is, here's a picture to scale. This is just an average sized person. And here's the big red ball. So the distance from around here to the other side is 3 meters. It has lots of diagnostic hardware. We have some plasma guns in case we want to insert plasma, and so on. Now, how are we trying to emulate the pulsar? Now, what is the goal of this experiment? And what I just described here to you, a neutron star is actually something very, very difficult to create. Therefore, we realized that we are not going to be able to make what the actual neutron star is. However, what we can emulate is the pulsar wind, the magnetosphere. The magnetosphere is just the plasma that's surrounding, the magnetized plasma that's surrounding this neutron star. So some of the goals of what we're going to see in the experiment is, first of all, this plasma wind, which I just described. If we set it to rotate, we should be able to see some plasma wind, some of the plasma go. Also a change in topology in which we are able to see how magnetic and how do they behave here with the plasma. We want to see fluctuations or turbulence. So turbulent motion, something that's going here on these magnetized winds. And we also want to see plasma heating, how the fact that we have here a magnetic field rotating energizes the plasma and heats it up. So, and this is a picture that we took here in which we have the RMF coils. RMF stands for rotating magnetic field. I'm going to get in a moment in a detail for that, which are just how we are going to create this magnetic field, and we expect to see this behavior of the experiment. So one thing I like is this picture. This picture pretty much summarizes the whole experiment of what we're trying to do. And let me tell you what it is. So as I just described here, this is the big red ball here to the right, this giant circle. We're going to have the coils. The coils are going to help us in creating the magnetic field that's going to be rotating, such as what we would expect in a pulsar. We're going to put plasma here, which plasma is going to now do its thing, create a pulsar wind, and so on. How we're going to feed these coils? How we're going to feed the RMF coils? It's here. This is the electronics. We expect to have some sort of or some source of energy in which we can divide it into two channels. One's going to be a sine channel, and the other one's going to be a cosine channel. For those of you who know math, these are trigonometric functions. So basically, what we're going to have, and for those of you who are into electronics, we're going to have a function generator with two channels, in which in one we can create a sine waveform, and the other one we can create a cosine waveform. We're going to connect one of the channels to some of the coils here, and we're going to connect the cosine channel to the rest of the coils here, at least for this first iteration, in which we want this magnetic field to be rotating around the equatorial plane. And you'll see a picture of that in a moment. So that takes us to the hardware development. Now, even though I described here the whole experiment, I'm going to focus mainly on the right here. What we need to have the plasma inside. The electronics is being developed. However, I'm going to focus just because of time on what's here on the right, which is mostly mechanical in its sense. So let's talk a little bit about hardware development. So this is a drawing of what we're trying to accomplish. This is how we imagine, again, because we don't want to emulate the nucleus or the actual neutron star. We just want to know what happens to the plasma around it. We're going to have something to create coils. Coils create magnetic fields. Well, because these coils cannot be in direct contact with the plasma, we need something to shield them from this plasma, especially because this plasma we expected to achieve high temperatures. So we need electronics, which are going to be here, mainly these cables creating magnetic field. We're going to have the coil form. The coil forms whatever is going to be holding them up here, whatever is going to give them this shape. And we're going to have what's called a vacuum vessel. This vacuum vessel, it's going to go inside the machine. So this is the big red ball, and this is the vacuum vessel, what's gray here. And the main job for the vacuum vessel is going to be shielding the coil form and all the electronics that goes inside here from being in contact with the plasma. So so more in detail, I'm going to describe here all these three steps or everything that's here in this lower picture. So the first one was the coil form. The coil form was taken directly from here from the drawing. How do we want it? And so what we did was 3D print the coil form. This is all 3D printed. As you can see here, we have some green here, which is going to be one of the channels, whether it is a sine or cosine, depending on what we decide at the moment. And the other ones has this gray color, in which we're going to have the sine or the cosine or whatever we choose on the other. This is going to have the other. So you can see here that we need to wind some cables here, and these cables are going to be connected here on the inside, and that's going to take. This is what's going to go inside the vacuum vessel. So next, so now we have the coil form. If we have the coil form, then what's next are going to be the cables. So for conductors, we chose lead wire. Through several studies, we found that lead wire may suit our needs in terms of what a conductor is and how the resistance they have, the inner inductance they have. And I'm going to get a little bit in a few slides on how much current we want and the magnetic field that we're aiming for. So what we did was took 4 strands, we winded them up, and with an insulator, which is basically just some tape here, we put them together. Now the next thing is to do some thinning tests. The thinning pretty much consists on removing here whatever insulator, whatever is not a conductor, and making the conductor visible here so that we can connect these ends to wherever we want the channels to gain the current from. So now that is something that's being done. We have the thinning test. We just have to wind the cables around this coil form. And the next step is going to be an analysis for a vacuum case. The vacuum case is that in which we have pretty much everything except for the plasma. So here we can see some numerical simulations of how we expect the magnetic field to behave. This is the coil form, and these are the channels, blue and red. And the simulations show some interesting results and what we would expect. I'm going to show you in a picture the time I'm going to show you in a slide the time evolution of this dipole, this magnetic field. But it pretty much resembles what we want for the pulsar's magnetic field. So here I have, this is the time evolution. Each square of these represents a different time of how the magnetic field behaves. You can see sort of the resemblance here to the picture to the right, in which first our magnetic field right here is pointing upwards. Now, as time progresses, the blue coil here starts turning off because of the cosine function, and the sine function starts turning up. So that is going to make the direction change from up here to going more towards the left. Eventually, this cosine function is going to completely turn off, leaving all power to the sine function. And the process is just something that repeats. Now the cosine turns on, but it turns out it starts pointing instead of upwards, downwards. And this is how we're going to create our magnetic field. Essentially, this experiment, as I mentioned, we only have these numerical analyses, which are pretty much just computer simulations. We're going to run them at 30 kiloamps at a frequency of 6 kilohertz. 6 kilohertz meaning that they should be able to do 6,000 turns per second. And the magnetic field that we expect right at the center is going to be of 795 Gauss. And just compared with Earth's magnetic field, Earth's magnetic field is approximately 0.45 Gauss. So this is for the moment what the computer simulations throw at us. Now that we have the coil form, we have the cables, we have the thinning test. We just need to wind up the cables. Then we need the vacuum vessel. So here at Whipple, we ordered an atmospheric pressure plastic vessel, which is from the original drawing here is this gray. This is fabricated of fiberglass reinforced plastic, on which the reason why we chose fiberglass reinforced plastic was because we did some vacuum tests to see, even though this is a plastic, some of the air might go from the inside here to the outside. There might be something in which the molecules pass. So we want the material that allows us to contaminate less our plasma environment inside BRB. And so what's currently being done with this vacuum vessel, this is the FRP. We're painting it right now. The painting is being done with aluminum oxide due to its good vacuum properties. And because when in contact with the plasma, it shouldn't cause any trouble. So that's why we chose that. And this is a rotated look of how it would look inside BRB. This is a picture that I already presented, but it's ultimately what we're trying to aim here in order to create our magnetic field. Now, I have described to you what we have done at the moment. Now, what are the future steps? So in the future steps, well, first of all, we have to finish and test the paint job on the vacuum vessel. Even aluminum oxide has some good properties. We still need to test it to make sure that we took the right decision in that painting. Afterwards, it's going to be set up these the coil form alongside the vacuum vessel inside BRB and conduct tests with both the RMF channels, both the sine and the cosine, and make sure that those vacuum results show at us the same as the computer simulations. Otherwise, redo the job and see how can we make it better. Afterwards, we want to implement the gas buffing system. Now, the gas buffing system is what's going to allow plasma to be in contact with this magnetic field and with the vacuum vessel. So we need to implement this gas buffing system, which is just going to puff ionized gas, aka a plasma, and we should be able to control the puffing into the vessel. Forward, we're trying to do some numerical simulations for the electromagnetic fields. As I mentioned, we want to study also the radiation here inside. So if we have a rotating magnetic field, how is the energy going to behave? How is the energy of those fields going to behave? And what can we predict in the vacuum case? And finally, we need to develop and integrate a third set of DC coil to allow for obliquity. Now, let me go back here. As you can see here, this magnetic field is only pointing in the equatorial direction, or it lies on the equatorial plane. However, what I showed you earlier about pulsars, the pulsars was lying not on the equatorial plane of the of the neutron star, but it has some obliquity, meaning it was at some angle between the equatorial plane and the axis of rotation. That set of coils is still to be developed. But that's pretty much it. That's where we are, and those are our future steps. Some acknowledgements. This is funded by the United States Department of Energy. Here are my references in case you want to learn more about the work we're doing, or what are we taking as a basis for this work. And so now that leaves me to the fact of something closer about me. As Daniel mentioned, I was born in Toluca, and something I believe is splendid about Toluca. Toluca is a city which is at high altitude, one of the highest cities in Mexico. It's about 2,500 meters above the sea. And Toluca lies just down of a volcano, of a dormant volcano. This volcano is named Nevada de Toluca, or as the locals call it, Chinantecatl. Chinantecatl means naked man. The volcano itself is like 40 minutes outside of Toluca. It's towards the west. And the highest peak is at 4,680 meters. So you can see it's somewhere around about here. Now, there's something also very interesting about this volcano. This volcano has been dormant for thousands of years, but there are lakes on the volcano. There are specifically two lakes, two main lakes: the Lake of the Sun, or Sun Lake, and the Moon Lake. The two lakes are about a height of 4,200 meters above sea level, which is pretty high. The Sun Lake, which is the largest one and is the one we are able to see here in the pictures. This is not necessarily winter. This is something that happens very commonly whenever it rains in Toluca. One of the things you see is how even though the rest of the area is just green, there's plenty of snow always at the volcano when it rains. So this is surely a picture after it has rained. This is maybe during summer time. Another thing is that archaeologists have been here, have found traces of clay and different things that have been offered, or that were offered and date like hundreds of years. So if they had been throwing things at the lake for sacrifices or something, it's still unsure as to why, but they keep finding more things as they dig deeper into the lakes. And thank you.